we have this equation. Compression ratio go up, efficiency go down. Okay. So the actual horsepower that you need depend on this volumetric efficiency too. Let's go back. Okay. Sometimes we have compression ratio of 5 or 6, but the recommendation is compression ratio less than 4 or equal to 4. The problem with too much compression ratio is it's getting hot. And when it's hot, it may catch fire easily. This year we didn't go to like CSI to see the compressor because we reduced the credit hours from 4 to 3, okay? But in CSI, in Midland, I saw the picture of, not just picture, the actual compressor that they catch on fire because it's getting too hot, right? So have compression ratio, low compression ratio means you didn't compress much. When you didn't compress much, it's not going to be that hot, okay? Right, compression ratio per stage. So we have final discharge pressure equal to first stage suction pressure. Everything has to be PSIA, okay, absolute value. Multiplied by R, which is the compression ratio per stage, raised to the power of n. This equation tells me that every stage have the same compression ratio. Okay? When we design the compressor, every stage must have the same compression ratio. We cannot do like first stage compression ratio equal to 3, second stage 4, third stage maybe 2.5. No, all of them has to be the same. If we do different compression ratio, do you know what happens? Okay, next to Ben. Is it Ben or Chris? Or Hunter? Colton. Okay, I'm sorry. Okay, next, what's your name, sir?
Colton.
Both of you are Colton, okay. Another Colton. What happened if your compression ratio per stage is not the same? What do you think happened?
You're either going to have to use more power or...
Oh, okay. See that you know it then. Why is that?
Because if your compression ratio is different, if you have a higher compression ratio, you're going to need more power to be able to compress it that much. Or
what directly happened to the interstage cooler? So if you have the same compression ratio, maybe you have to look at the temperature. There's a formula to calculate temperature. I'm sorry, I just keep moving around. I will tell you the slide number. This is slide 36. Okay. Temperature ratio is directly proportionate to compression ratio. Temperature ratio has a direct relationship with pressure ratio. So it is T1 over T2, T2 over T1 equal to P2 over P1 over some value. Okay. I'm trying to go back. Okay. So if we have different compression ratio, the discharge temperature will not be the same. Okay, discharge temperature will not be the same. We have constant mass flow rate. Jayanti, can you go restart the camera? Or you did that already? Okay, we move at the constant mass flow rate. Okay, mass flow rate through the compressor is constant. If a certain state is hotter than usual, this means we require more cooling for that particular state. Make sense? Because if the temperature go up, the required energy or the required cooling will equal to the change in the enthalpy, which is directly like mCp delta T. More or less mCp delta T, right? Mass flow rate multiplied by the difference in temperature. Okay? But we use the same radiator at the back, right? So are we going to do like more pass for one stage or less pass for another stage? That's difficult to design, right? To make everything easy and make it efficient, compression ratio per stage of every stage must be the same. Okay, good. Alright, do the math. We get compression ratio per stage equal to discharge pressure over suction pressure. That is discharge pressure of the last stage. Suction pressure of the first stage multiplied by 1 over n. Okay, n is number of stages required. Okay, let's take a look at one quick example to clarify that. Suction pressure is 20 psi. The required discharge pressure is 1000 psi. Okay, we try to save the gas, and one of the requirement may be 1000 psi. How many stages do we need? Okay, how many stages do we need? If we assume that we need 3 stages, what happens? Okay, need to have 3 stages of compression. We assume that we have 3 stages of the compression. What is the compression ratio? Plug the number in 1000 over 20 raised to power 1 over 3 and get 3.684. That is number of stage. Compression ratio. So how do we know how many stages we want? How do we know how many? If I want to go from 20 to 1000, how many stages do I want? Or how do I know that? Step number one, I need to know the requirement on the compression ratio for the design. Okay, the requirement for the compression ratio for the design, it varies, but the recommendation may be 3 to 4, okay, or less than 4. So if you want to do something that less than 4, how do we know that it's less than 4? We do trial and error. Put one stage, put number 1 over there, and what do you get? So that is 50, compression ratio of 50. If you use a single stage, the compression ratio of that stage has to be 50 to do anything. That's too much, right? So put number 2 over there. I get what was that? Square root of 50. About 7. 7 multiplied by 7 is 49. So compression ratio per stage is 7. If I have 2 stages, that's too much, more than 4. We don't like it, right? So we put number 3 in, and number 3 happens to be that much. Then I know, hey, we have to have at least 3. At least 3, okay? So how do I get those numbers? Next to colon, what's your answer?
Ron.
Ron?
Yeah.
Where I know that is first stage, suction, and that is the final stage, discharge. Ron, how do I get 73.7? Where does that come from? Next to Ron, what's your answer? Braxton. Can you use this number, that formula to do anything? Braxton?
You have to go to the chart, right?
Okay, how do you get 73.7? 20 multiplied by?
Plug your R in and use any.
Braxton?
I have a question. You have to multiply by the stages, right?
So we have 20 multiplied by 3.684, then I get that. You believe me? Let's try that. You get that?
Yes. When you have stages, does the stage have to be a whole number?
Number of stage has to be the whole number. Yes. Number of stage has to be, it's like, I cannot design for 2.5 stage, okay? You see, a compressed half time, there's nothing like that. Or I have a half of the compressor. So 20 multiplied by that, I get 73.7. Okay, that gives us a real anyway. Okay, 73.7 multiplied by that number again, I get that much. And that multiplied by that again, I get that much. What are these numbers? Is it the discharge of each stage? Is it? Yes, okay. With the assumption that there's no pressure drop between stage 1 and stage 2. So discharge of stage 1 is 73.7. It goes to cooling unit, okay? And then when you go back, there's no pressure drop. Then it stays the same. That is Discharge of stage 1 equal to suction of stage 2. That's the assumption to do all this calculation. Question for me. Okay, now you get how to do how many stages, you can tell how many horsepower. Then you can buy this compressor already. You like it? Yes, it's just that. But there are other way other than using the chart for the calculated total horsepower. Let's take a look a little bit closer for 2 stages to see why do we want to cool it down. Okay. You see this? I put the less total area under the graph. I have pressure and volume. Area under the graph represents kind of horsepower or energy required to do the compression. So if I don't cool it down, the area look like that. If I cool it down, you look at A to D. What happens between A and D? Colon and colon. What happens between C, A and D? A to D. What happens between A to D? Change in volume. Volume goes down. Pressure stays the same. How can that happen, Ron? A have higher volume and B have less volume. But what is the trick over there to make the volume change? Pressure stays the same. Cooling, yeah. We cool it down, then we go from A to B. So this is the law of interstage. Then we compress it again, it go up, okay. Then from C to this point, volume go down, pressure stay the same. It's not like really cooling, it's like we release the gas to the outlet or something, and we have repeat this process, right? When you go back everything, it repeat this kind of process. From 2 to 3, discharge valve open and we release some gas out. That's what it is, okay? So we have cooling. All right. Because of cooling, we have less cross-section area, and that requires less power. In the diagram, okay, gas coming in, go to number 1, inlet scrubber, remove any liquid, then it go to number 2, which is compressor, like a reciprocating compressor. We compress it, so we go number 1, this A, after we leave the inlet scrubber, we compress it, pressure go up with a constant entropy. That must be theoretical value. So we go to point B. When we reach point B, A and B is before and after compression. After the compression, pressure go up, entropy stay the same. Then we cool it down. Okay, that's interstage cooler. When we cool it down, we cool it down without losing pressure. Okay, so we follow the constant pressure line, but temperature go down. Okay, we reach point C. Once we reach point C, we go to another inlet scrubber. Okay, Ron, and what's your name after Ron? Braxton. Oh, your name is Ron?
No, it's Braxton.
Go back and look at their ID. Come on. See who's Ron, who's Braxton. Okay, next to Ron and Braxton, what's your name?
Braxton.
Israel or?
Yeah.
Yes, Israel. Okay, when we go from C to D, but we need to have another scrubber again. So which person is Ron? On the left and Braxton on the right. Okay, very good. I'll try to memorize that. Israel, why do we need inlet scrubber again? Why do we need inlet scrubber again? We already have it. Why do we have to do it again? You like your friend's suggestion? Ask him. What did he say?
He's got an answer for you.
Oh, what's your name, sir?
Sam, after you cool it, you might have to gas liquid or something.
It will.
Yeah.
It's not just mine. That's why they need to put it over there. So, what's your name again? Huh?
Rada.
So we have that again. We compress it, pressure go up, we cool it down, temperature go down. It's like that. And we have trouble again, and then we have dry gas with high pressure. Okay, so look at D and A. Temperature is about the same, but the pressure go up. Any question for me about this? This means when we design compressor, it needs interstage cooler. If you don't put interstage cooler in the compressor question, even though I don't tell you, you get zero. It's wrong. Okay? Interstage cooler needs multi-stage compression needs interstage cooler. Okay, let's take a look at this cooling heating gas at constant pressure. This example, let me read it for you. What is the amount of heat that must be removed in cooling 1 pound mole of 0.6 specific gravity natural gas at 200 psi from that much to that much? Why do we need to know this amount of heat? What is that for? Next to radar, what's your name, sir? Colton?
It's Trevor.
What?
We are all clear.
What is his name?
It's Trevor.
Trevor. Okay, Trevor. Why do we have to do this? What is that for? Why do we need to know the amount of heat? When do we cool it down at constant temperature? Does it happen in the interstage cooler? Yes. Question A is related to the design of the heat exchanger in the back, or the aerial cooler, or the radiator in the back. How big is the radiator you need? We don't know until we get that number. Okay? And I don't tell you how to design it. I don't know it myself, but the guy who buy this will need to know how many turns do we need, how many fins do we need. They need that number. How many BTU do you want to remove? Okay? So what is the cooling capacity do we need? So this is a calculation. We have 1 pound mole. We cool it down at constant pressure. Okay, and we get that number. Where does that number come from? Okay, let's take a look at this. So we have cool it down from 600 to 100. 600 at 200 psi. So this is the line of 200 psi. Right? We use a model diagram. We start at 600, so that is 600. So we start at that point. We try to cool it down to 100. 100 is that. This is the 100 line. Okay. We try to cool it down from that to that point. Constant pressure. Okay. This happens in the interstage cooler. We read the specific enthalpy on the left, then calculate the difference. That number is used in the design of the radiator. How big should it be? It comes from that. Or how much is the cooling capacity? It comes from that. So we have BTU per pound mole minus BTU per pound mole. It's not BTU per standard cubic foot yet. You can do that conversion, can you? Right? So we get that number, BTU per pound mole, 5,600. Okay, let's take a look at question B. If this gas is then heated from 100 to 300 Fahrenheit, how much heat is required per pound mole? So we do the same thing. Let's go up and read the value under this. So now we know how to calculate the amount of heat required to cool it down at constant pressure or to heat it up at constant pressure. When do we heat it up at constant pressure? Next to Trevor. What was your name?
Joe.
Joe. In what situation that we heat the gas at a constant pressure? Joe.
After it gets
Which equipment that we do that?
line heater.
Line heater, correct. Okay. In the line heater.
Can I ask you a different question real quick?
Yes,
Can you
yes.
go back to one slide, please?
This.
You got it.
One more.
Right there. How are you cooling a gas at constant pressure?
How do we cool gas at constant pressure? How do we do that? You see this thing?
Yeah.
That's a radiator or cooler. The way it works is it has a pipe move in there, like you see in the field trip, and that pipe has a fin around it. Many of them. You remember when you saw in the field trip? What happened is there's a fan over here, blow the air, atmospheric air across it. So when air, it's like heat sink in the CPU or computer. When the air blow across it, the temperature drops.
No,
That's how
I
they cool
get
it.
how it's cooled.
At constant pressure?
Yeah, yeah.
Okay, when there's a gas moving inside that pipe. Okay, there's a gas moving inside that pipe. When we cool it down from the outside, okay, we cool it down from the outside, the temperature drops. Okay, but the pressure stays almost the same. It's not the same, but it's quite the same. Because if we to manage to have the drop in pressure, if we have a long pipe, we flow gas in, we will have pressure drop. Okay, flow in a pipe, we always have pressure drop. So we need to have big enough size. Okay, number one. Number two, every turn, like in this interstate cooler, it has this, right? Every turn, there will be pressure drop. Okay, so the pressure drop could be 2 psi, 5% or something. So it's not really constant pressure. In the pipe, there is no restrictions. There is no plate or nothing to restrict it. So it flows while it maintains the pressure.
How's the volume changing?
Volume, volume go down. Volume go down. Like that, volume go down. So when you're talking about the impact of shrinking on the pressure, right? What happens when gas flow and it shrinks? So that we didn't study yet, but there are two scenarios, okay? If we have, let's take a look at this. Expansion, slow expansion. In a slow expansion, like gradual and slow expansion, we have gas coming in. Velocity at this point is less, far away from the inlet is less than the velocity at the inlet. Velocity go down because it's kind of expanding to preserve that. When velocity go down, this thing from the Bernoulli law, the pressure, instead of drop, we gain pressure. We kind of gain pressure, okay? But if the expansion is quick, like this, there's a detachment from the flow boundary is like not attached to this always, and it's have the edges over here. So we actually have pressure drop if the expansion is not that slow. So flow with the expansion by itself because of temperature. So we flow slow and later on we flow quick like that. That will be accelerational pressure loss. Accelerational pressure loss because they're expansion. So if we flow it quick and we shrink it and we flow slow over here, there will be deceleration pressure gain. But those things is negligible compared to the amount of energy or force that you put in. So the accelerational pressure gain is not much, okay, we neglect it. The only time that is kind of significant is below 100 psi. Okay, it can be significant. So for the compressor calculation, they neglect that. Does that answer your question? Yes, it no way on earth that they can make that theoretically perfect. No pressure drop or pressure gain because there is a shrinking volume or there's a shrinking volume. So there is a like different in the pressure, a little bit pressure gain and every turn is not pressure drop, but they neglect all that. Okay? Because it's small. Let me add. Oh, we didn't do that yet. Alright. So this is kind of similar to line heater calculation too, right? Is it? Is it similar to line heater calculation? Increase the temperature at the constant pressure. That's kind of line heater. But in the line heater, we will worry about the hydrate line too. Right? All right, any question on these two examples? No, right? Let's move on. Conservation of energy. Okay. I'll show you this quickly. Okay, this will be for grad level. For undergrad level, we don't really go through the derivation, but I at least tell you where does it come from and what is the assumption associated with it. To derive, the end product is this. To derive this formula, see, isentropic horsepower formula, you already use the shaft, right? The shaft. But, you know, each shaft is for a certain specific gravity, is for a certain type of gas. If you want something that is specific to your case, let's say you have different K value, you have different temperature that is coming in or something. So this will be more specific for your case. And within the shaft, I use eyeball, it may like have some error. This will be a little bit more accurate, okay? To derive this isentropic horsepower or analytical method, we go through several hoops over here. From conservation of energy, okay, they have several terms. This is for steady state system. There's a mass in and mass out, but it's steady state, no change with time. So each term, you read it, it's a chemical potential term, it's have the work term due to change in volume, and so on. They neglect, okay, several other terms, and neglect the chemical potential term, surface energy term, elevation term, okay, assume the change in kinetic energy, potential energy, and energy loss is neglected. You see energy loss, Joe? The deceleration, move in the turn, everything, they neglect all that, okay? So when they make the change in the kinetic energy, potential energy, they come up with this equation and do isentropic process, PV to the power of K equal to constant, do a lot more math, and more math, and a little bit more math, and more math, then we get that. Okay? Your job is to understand what is this equation assumption. The assumption is this is for isentropic horsepower, constant S. It neglects all the loss, it neglects all the elevation change, it neglects all the kinetic energy change. Okay? That's your job. And we have final equation as this. Before the final equation, you can see that, okay, it have been, theoretically, we get this equation first, which you don't know how do we get that because I didn't show you any math. The math is previous page. Right? We get that equation, and we have some improvement, okay? Theoretically, it doesn't have Z value over here, but now it's pop up, you see? That is like empirically modified to add this, okay? And we change the unit work compression per unit mass, power force foot per power mass. Power force foot per power mass is not like convenient to use, what do you think? So they eventually change to horsepower per gas flow rate instead of power force foot per power mass. What was that? Power force foot per power mass doesn't mean much for us, right? But this horsepower and maintenance characteristic foot that we need. So this means if we want more flow rate. Oh, okay, next to Joe Marty. When we have, okay, 2 M S C F D. So does it mean that we flow at constant mass flow rate? Or we flow it at constant volumetric flow rate? Do we flow at constant mass flow rate or not? Okay, next to Marty. No. Who agree with her? Okay, let's say your friend next to you. What's your name, ma'am?
She's not my friend.
Sorry, you're, I mean, what do you call it? Colleagues or another person that coexists next to you? Okay. Elizabeth?
Yes.
Okay. When we have two MMSCFD, do we have constant mass flow rate? True or false? Oh, you disagree with her? Okay. What about you? Next, what's your name, sir?
James,
James. Is it 2 mmSCFD? Is that constant mass flow rate?
I guess.
Okay. I think it is. Why do I say that? Even though it's a unit of volume, but it is the volume at 60 Fahrenheit and 14.65 psi for Texas. So it's a volume at a certain condition. So that volume at that condition is constant mass.
I thought you said there's no temperature loss, or,
When we have S, you see that S. That S standard condition, we refer to 60 Fahrenheit and 14.65 for Texas, or 14.7, it depends on how we define the standard. But with that S, it means it's at a certain pressure and temperature. At that pressure and temperature, we have a certain amount of mass. You agree? So this means this is also constant mass flow rate. Okay? This is a mass or volume at the standard condition. It's kind of the same thing. So this means you can convert this mmSCFD to power per second. Okay? Can you? Yes, it's the same thing. mmSCFD can be converted to power per second, power per hour, or something, independent of mass. Alright, we talk about that because horsepower required depends on amount of mass that go through. If you compress more mass, more material, we require more work. Okay? So this equation gives us W bar minus W bar is what do we need by minus sign? James?
What?
Why do we need that minus sign? To make everything positive or something? You try that, okay? W by itself is work done by the system, I believe, okay? Put minus sign over there will be work done on the system, okay? So whatever you do, this thing is positive and it's work done on the system. So it's a work done on the system described in power per mass flow rate or horsepower per mmCFD. Okay? Actually, this should be SCFD. It's not just it's MMSCFD, standard condition, defined as TB, temperature, and PB, pressure, base pressure and base temperature. Alright, this means if you know, this is per stage, okay, not total, this is per stage. P1 is inlet of stage 1. P2 is discharge of stage 1. We do everything just one stage. If we have multiple stages, we do this several times and add them together. We don't put P1 as a first stage and P2 as a final stage. Because when we have multi-stage, it's reduce the amount of energy required than compared to just go from 1 and compression ratio of 50. You see what I'm saying? What about T1? T1 is the suction temperature of stage 1. How do you know the suction temperature of stage 2? Okay, next to James, what's your name, sir?
Sean.
Sean? Okay. Same name? Who else is Sean? Sean. That's Joe. Alright, Sean. How do you know the suction temperature of stage 2?
Probably look it up on a graph.
Okay. Next from Sean, what's your name, sir? Chris. How do you know suction temperature of stage 2? Okay, question is, suction temperature of stage 2, is that the same as discharge temperature of stage 1? Chris? Yes, raise your hand. Who else is his friend? Raise your hand. Yeah. Wrong, okay? Suction temperature of stage 2 must not be the same as discharge temperature of stage 1 because we have interstage cooler. We always need to have interstage cooler. And in the typical design, you can assume that suction temperature of stage 2 is the same as suction temperature of stage 1 if you don't have any number. Okay? So let's say the gas is cool, come in at 80. We compress it, the temperature go up to 250 Fahrenheit. We cool it down. When we cool it down, we may cool it down to 80 or we may cool it down to just 100. It may not be 80. So when we cool it down to 100, then the second stage, right? The third stage, when it cool down, it will go back to 100 again. See what I'm saying? It will repeat itself. So even though we start at 80, the temperature go up to 50, we go down. Maybe sometimes in the stage cooler doesn't cool that much and it becomes just 100. We compress it again, we cool down again, we try to cool down to the same temperature. The reason that it's the same temperature because we use same compression ratio per stage. Okay? Alright. This is per stage. If you have multiple stages, add them together. Okay? If you don't have any number given, just the inlet temperature, you may assume 100 F. Okay? Why don't we say, so the discharge temperature of stage 2, suction temperature of stage 2 cannot be lower than the ambient temperature. Agree? Chris? Why is that?
Because it's inside the
Can it be lower than the ambient temperature? What's your comment?
You're cooling it with an ambient temperature intercooler, so you're not going to get it lower than
Yeah. Correct. Yeah. We use the ambient temperature to cool it down, right? So it cannot be lower than that. Good? Alright, the rest is just put the number in and do the calculation, add them together. So the part that we don't know yet is about K value. How do we get K value? I have 2 more minutes. Okay, let's finish the K value. For ideal gas, we have CV equal to Cp minus R. Okay, the unit of specific heat is the same of R unit. Okay. Quick calculation is this ratio of K equal to Cp over 1.986. Okay. If we have single component. If we have multiple components and we want to do it very accurate, we do weighted average based on the molecular weight. But if we don't have those things, this thing could be difficult to use because we need to know the mole fraction or something. We use like the computer program use that, but what you actually use is this formula, okay? Because we just deal with natural gas. If the specific gravity in this range, we use this formula for K at 150. If the step, that's it. Then we don't have K at other values. Okay, this is how we get K value. And discharge temperature, in addition to calculate from the chart or read from the chart, we have this formula to get the actual number that require reading from the chart. Okay, the rest. Oh, okay, you get a little bit there. Okay, thank you for coming. See you next time. Please do the homework. Just start. Try to come see us now on me.
I'll just eat. I mean, it's like an 8 hour. Yeah. No, like only which is 8 hours. Fast, like,